Very happy to start a new fall series of Warren lectures, and it's a great pleasure to have a first talk to be given by an old friend of the department who has been here on a number of occasions, Professor Greg Rodin from University of Texas at Austin. Greg, even as I said, is an old friend, but there are new students and some new faculty, so I would do a very short introduction. Greg is originally from Russia, but it was long ago where he got his undergraduate education in a very well-established polytechnical institute at that time of St. Petersburg. It's very famous for its School of Mechanics. We had some visitors from the university and had a student also. Then he got his master's and PhD at MIT. He relocated to the United States, so his graduate school work is at MIT. And in 1986, he joined the University of Texas at Austin, where he is now a full professor at Department of Aerospace and Engineering Mechanics. Area of expertise, Greg's area of expertise are large, complex problems in mechanics of solids and fluids. He worked on a number of various topics. He is very a good speaker, was invited numerous times, different universities all over the world. And with that, I would not go any further because most of you already know Greg. So I'll save some time and introduce, give the podium to Greg. Please join me in welcoming.
Thank you very much, Sonia. Thank you for inviting me. It's a pleasure to be here always. Also, I was very impressed with the list of Warren speakers. Especially there's this, I think, your invitee, a smaller professor from Harvard, Jim Rice, who is my academic grandfather. And so, at any rate, I'm indeed a member of the aerospace engineering department, but if you're not a biomedical engineer, I'll be talking about pasta. All right? My good friend Roberto Bellerini is not here, so I can talk about pasta. But Jimmy, now he's Dr. Carlton. He's at Sandia National Labs. He defended in July. And a lot of stuff that I'll be talking here is part of his PhD dissertation. So, let me see. Yeah, good. All right. So I work together with Michael Sachs, who is a biomedical engineer, and he is interested in artificial tissues. And artificial tissues are there to repair hearts, right, particular leaflets, right? And if we look a bit deeper or at a finer scale, we see that a lot of native tissues formed by fibrous structures, and there is a biological matter that surrounds it. And so pretty much we may think about fibers embedded into a biological matrix as a composite. And of course, this structure led to the development of artificial materials that mimic the properties, right? And the properties and the structure. So at this stage, the structure is mimicked reasonably well. The properties are not there. So there are no artificial tissues that could really compete in mechanical terms with the natural tissue. But at any rate, we have to begin somewhere. And so the way things work is that one of the techniques is essentially a machine that spits out polymeric fibers. And these polymeric fibers form a scaffold. And eventually, this scaffold will be filled with cells that will be growing. And then we will get something that looks like this, that will resemble leaflets or any really other component that we may think about in terms of biomedical replacements. Okay. Now, why do we want to study mechanics of this? Let me make it perfectly clear. This is not mechanics of composites where we're concerned with stresses and strains and overall properties. The main reason for mechanics in this class of problem is the following, that when we grow biological cells filling the space, we want to exercise them. And the exercising occurs through mechanical loading, and we cycle these materials, and the cycling process is absolutely critical for developing a healthy biomass and a healthy tissue. And so the long-term goal of all such things is to develop tissue, and developing tissue is done through mechanical loading. So I'm not going to talk about kind of computing overall properties or anything like that. So the theme is somewhat different, okay? We're at a stage where we try to understand how these things work, okay? And in a kind of at a later stage, we hope to really connect it to models that involve the cells. So here we are. We start with this thing, which is microscopic fibers, anywhere 1 to 10 microns. So fibers could be even in submicron size. The individual features could be, let's say, 10 microns, pores, all right? And of course, at the heart level, we deal with something in the centimeter range. And we want to have a mesoscopic understanding of how to go from here to here. And that's another kind of way to look at it. So we're moving towards simpler models. I will start with describing basic geometry because, believe it or not, this is something that is not as well understood in the field as one would hope. So I will start with a monolayer. And here's an important thing, okay? If you look at the picture and if you think about that this is indeed some kind of random collection of fibers, and I have this is computer generated, of course, randomness. The first thing you need to know about random walks, that random walks in 2D and 3D are completely different animals. In 2D, they're relatively easy, and as a matter of fact, when you talk about fibers, you can talk about lines, and the story is very good. You can tell everything in terms of lines, and then you can assign a diameter, whatever diameter your heart desires, but the line itself will do fine, and you will have plenty of intersections and things like that. If you have a walk in 3D and you do not assign the diameter, the walk will never intersect itself. It just will get lost. It will not find, right? And so thinking about geometry in 2D is much easier because obviously we don't have to worry about how to intersect things. And so I would like to understand what happens at a monolayer, okay? And then, of course, I will put a bunch of monolayers to form a multi-layered structures. And it will be pretty consistent with what we really see because this electrospinning produces naturally layered structures, right? If you indeed want to think about pasta making, you have a pasta making machine and pasta kind of naturally falls on the table and goes layer by layer. That's a good picture, right? If you want to understand, if you're a biomedical engineer, please, I insincerely apologize, but I told it many times to Michael, and Michael gets a bit upset at me, but we're still friends. So let's talk about measurements. What do we want to measure? Okay? We want to measure a lot of things, So we want to see contacts, distances, angle between contacts, pore sizes, shapes, because all of this stuff somehow will contribute to stress transmission eventually to the cells. What is easy to measure? Total fiber length. You can weigh it or you can check the machine, right? What is also easy to measure is orientation density function. So if I have fibers, pretty much, I don't need to distinguish individual segments. Really, I can construct this function by doing fairly basic measurements. So our first task is the following. Can I say something about this part of the list in terms of these two parameters, right? Moreover, it seems like a natural thing to do to choose as the key internal variables if I want to think about continuum models, right? So I would like to talk a little bit about geometric probability. Buffon lived more than 200 years ago, and he solved a very charming problem. You have a plane covered with lines, equispaced lines, and then you throw a segment right on that plane, and you count how many intersections you have. Okay. So the problem that I would like to solve looks a little bit different, right? I'm interested in having m segments of the same length. They're randomly thrown on the plane over an area A, and I would like to figure out what is the probability that at least one segment intersect a test line segment tau. So the red guy is the test segment, right? And I just be using it to probe the population of short segments. Now, it is very easy to kind of argue that if my test segment has an orientation phi, and the segment of interest, S, the green guy, right, has an angle phi prime such that the angle between these two guys is the absolute value of phi minus phi prime, then as long as the green guy lies, the center of the green guy lies inside of this parallelogram, then it will intersect the red segment. And so pretty much then the calculation looks like this. If I look at the probability, let's see what we have here, all right? This is the area of the parallelogram. This is area occupied by all the segments. So the probability of finding, let's say, the ratio of the areas, right, is given by this term. And now what I have another thing. F is the probability density function, all right, times delta phi. This tells us what portion of the segments have the orientation angle phi prime, all right? So this is inside the parallelogram, and this is the properly oriented segment. And when I calculate the probability, I just simply calculate, integrate, and I have this expression, right? This is for one segment. If I have probability of n intersections, I have Poisson process, I'll get something like this. And the mean value for having n intersections with the segment is given by this formula. Okay. What is the key in terms of, what do we really need to take home? Okay. Please take a look at what we have here in front of the integral, and that really will be very important. Okay. So first, let me go back and say I will divide this mu n by L sub t. And when I do that, that should be Yeah, that's correct. Right. So this will be the linear intersection density along the segment oriented at the angle phi, right? So this is 1 over length. The other thing that is left is linear fiber density. Linear fiber density is the length over the area. It's 1 over meter, okay? And in 2 dimensions, it turns out to be the natural parameter. Not the volume fraction, but 1 over meter. I could have the volume, because the volume fraction will be attached to a particular diameter. This thing is not attached to any diameter, and if you've seen things about dislocation mechanics, is this here, right? It's not a dimensionless quantity, it's length per area in 2D, right? And so this is very important thing, right? And this parameter psi I will keep around, okay? And then I can calculate pretty much what is mean linear intersection density, and you see it's scaled with psi. And then aerial intersection density, I just do another integration, and it's scaled with psi squared. And here I wrote the expressions, what it is for isotropically distributed fibers. In other words, when F is 1 over P, right? Then I can calculate these integrals, and I get this. Now, intuitively, what this means is the following. If you want to think about your specimen size, you don't think about how big it should be. Rather, you think about how densely it should be packed. And I talked to Boyan earlier today, and actually, you know, we had an interesting discussion. He looked at it from a different angle, but I think we're on board with this conclusion. Okay. Now, I have these formulas, but now these formulas are kind of good checks. But what I would like to do, I would like now to create an algorithm that will allow me to do mechanical simulations. And the algorithm is nothing but a bunch of random walks. Each fiber is a piecewise straight line, right? And each segment in the fiber can respect to its predecessor, but the rotation is limited. So I decide on how to limit it. And I put it all together, right? And it's a periodic array. And these are 2 examples. And I want to demonstrate that in this example, we have tortuous fibers, right? And here are quasi-straight fibers. And the difference between these 2 is controlling the rotation of the segment. Okay? So we can take this algorithm and we can create random walks and pretty much control a lot of things. And first exercise was to see really how many fibers we want to get to achieve what we want, right? Or to achieve representative properties. Here's normalized box length, normalized by this density, right? This measures the normalized areal of intersection density. So this tells us 1 over meter squared, how many intersections we have per unit area, or how many contacts, all right, of the fibers. And you can see that the dotted line is the asymptotic, is the analytical result, and you can see how simulations approach you know, the desired result, and roughly when the box reaches this 250, right, dimensionless size, we get somewhere close. There are also issues related to not only the box size, but also how well in our simulations we can achieve the target or DF, or the target orientation density function. So when we form the fibers, we do not necessarily get the isotropic or very close to isotropic. It takes some effort to get there. And here's the next picture that shows that what it takes, all right? And so in this picture, the white bars are the targets, right? We say we want to create a specimen with the target distribution, and the black bars is what it takes, the actual one, and the boxes that are really needed for this quite often could be very large, 600 units, all right? That's this, the box size time Xi, times Xi. This is not Xi minus 1. Xi is, that's a mistake. Okay, so we have this algorithm, and of course the next thing to do is, it's a biomedical business, you have to compute with, compare with experiments. That was very disheartening. We have 0.32, we got from the measurements 0.6. We spent quite a bit of time in trying to figure out where the factor of 2 is missing. Once we exhausted, we called the fellow who got 0.6, and we say, we have problems. Could you check? Oh, he said, very good. This I got by looking at the images, but I just developed a great program that allows me to computerize the reading from the micrographs. And so I'm looking at all of these pictures now. No, 0.6 was computer count. This is human count. This gives you an idea how hard the field is in terms of getting the data, all right? And the reason it's hard is because if you look at an image, let me show you a picture of an image like that. And if I ask you to compute the contacts in the layer, you see roughly 10 layers deep. And it's very difficult to decide which contact is in which layer. So, but the nice thing about working with Michael, he has a good sense of humor. And at some point I said, why don't we hire undergraduate students to deal with the problem? You see, there are 5 students. We gave them the same photographs, gave them the same instructions in the same room, and told them, could you please count? All this stuff here, the top line is theoretical, then everything but black points are all kinds of simulations, right? And I'm not going to go into details, it doesn't matter. The black points are humans, right? And you can see that, it's not a clean data, right? There is significant difference in terms of the counts, and the only thing they were asked to count is count the number of intersections. So, we kind of felt pretty good that we have a simulation tool that will allow us to go into the business of simulating. Okay. Now, here's a picture of a multi-layered thing. The coloring here is to indicate that we have 40 layers, right? So, and the way this thing was generated, you produce layer by layer, and then you superpose layers such that neighboring layers can form contacts with the fibers, with the neighbors, right? And this is not exactly abacus type of run, all right? You need to run it in parallel. I had another picture which was showing colors when you do partitioning, on processors. But a lot of computations were done here. They're large-scale computations done in parallel. That's point number 1. Okay. Then let's talk a little bit about what went into modeling assumptions. All right. So I take fibers, I assign them mechanical properties and diameters. Okay. Fibers are cast rods. I could have talked for a long time and give really detailed and boring speech about Coursera rods. They're not easy things. I'm not going to tell you anything about it. It's something that is pretty well established, and it was a matter of figuring out which theory to take. And we picked something that is reasonable, and let's say it's a hybrid of what we found in the literature. But I'm not going to advocate it as much better than anything else. It's just we liked it. Okay. In plane periodic boundary conditions, plane stress or no stress in the transverse directions. Intersections are welded. It means that there's no slip or no relative rotation in the contact. We don't take content deformation into account. What this means that if the fiber kind of initially doesn't contact any fiber and there is a contact, we just disregard that thing, we let them go, right? We use linear force versus elongation relationship as constitutive equations for the fibers. Okay, so these are the basic things. I may have missed something, from the list, but feel free to ask questions if you need more details about what went into simulations. Okay, what are the issues? Representative specimen size. And representative specimen size I have already discussed briefly. It could be in terms of geometric characteristics, right? But also in terms of mechanical characteristics. Single layer versus multi-layer response, okay? So obviously it will be nice if we could deal with single layers in order to analyze our problem rather than multi-layers, okay? That's very interesting. Tensile versus bending deformation mechanisms, right? My degree, undergraduate degree, is in civil engineering, and I understand perfectly well what's the difference between a frame and a truss. I teach statics. Guys, these are frames. Why? Because when two fibers intersect, right, you form something that naturally leads to kind of square cells, right, or quadrilateral cells rather than triangular cells. But, you live and learn, so I'll talk about this a bit. Affinity. Affinity in this setting means the following. If I subject a scaffold to some macroscopic deformation, right, how much the fibers understand about this deformation versus kind of without any interference from the neighbors versus the interference. So if the fibers do not interact or do not interfere, then we have perfect affinity. Each fiber does whatever we get from the macroscopic strain. And again, I want to emphasize that this needs to be kind of, this could be important, but we didn't do it. And so I can't really comment much on that. Yeah. Here's representative specimen sizes, that how these guys look like. 50, 100, 200. And we did a lot of simulations. We put a lot of statistics on this. And roughly, that's where the story goes. Okay. So I plot the strain energy density, right, normalized by the specimen size. Here is the number of realizations, all right? And I have three boxes, 50, 100, and 200. And you could recognize them by the symbols, by the colors. right? And the bars will show you standard deviation. And pretty much it's absolutely clear that you really don't need much to get to the nice region for statistics where more or less statistics doesn't matter, right? You can use boxes of size 50 and you can acquire statistics from a small number of specimens. So there are no surprises here in mechanical terms. Of course, as I mentioned earlier, it's very important to have large specimens to generate the proper statistics for the irritation density properties. Boxes of size 50 are pretty good. Single layer versus multi-layer response. Okay, so here we go. A single layer. Then what we did, we put together 10 layers. All right. And in these two cases, we kept the same volume fraction, ODF, fiber properties, and total fiber length. That's why this guy is a bit smaller. This is about 200, and this is about 65. And that's what will give me 65 squared times 10 will give me roughly 200 squared, right? That's where these ratios are. And we subjected these things to biaxial strain, equal biaxial strain, and here are the results. It is absolutely clear that, okay, we have pretty biaxial situation here, right? Isotropic material. We have plot stresses. It's a, second Piola Kirchhoff, PXX, PYY, and, all curves collapse. So basically, A, we have an isotropic story. B, the difference between this case for a monolayer versus 10-layer is immaterial, right? We're getting the same response. We tried other loadings, and that's also true. Now, what this tells us immediately is the following. If I look at multi-layers, because the fibers from each layer are in contact with the fibers from adjacent layers, the distance between contacts in multi-layered structures are small. They're a factor of 2 or 3 roughly, smaller than here, because here there are no additional contacts coming from the neighboring layers. If the distance between contacts is immaterial, but the fiber fraction matters, then you say, look, the bending deformation play a role, because the bending deformation is very sensitive to the length of the beam. And that gave us this indication. And to follow up on this, we just calculated what is the ratio of the axial energy to the bending energy. This is the stretch, right? So we went 1.5, so it's roughly 50% strain. And as you can see, only at the very beginning there is anything going on for the bending energy. At the end of the test, all right, there are 3 orders of magnitude. So I mentioned, right, that this is a frame. Yes? Frame is dominated by bending energy. There is no question about it. But this is a weird frame in the sense that these guys are very flexible. They actually have some tortuosity. And what they do, they realign themselves in such a way that you pretty much stretch a bunch of straight fibers, right, in uniaxial tension. Another bunch of fibers actually not only doesn't work, it tends to buckle, right? And so it very quickly reconfigures itself from a kind of frame-like structure to essentially bunch of power lines that transmit axial stresses, line stresses, and the rest of it is not functioning. Okay. And I will come back to this a little bit later, but let me talk about affinity of evolving ODFs. Okay. So here we are, start with an ODF, right, of a specimen, right, unloaded. It's a polar plot, so I plot radius, polar radius, right, versus angle. Okay, there has to be 180-degree symmetry, obviously, in these plots. And now what we do, we load such that there is a combination of biaxial strain and shearing, all right? And the principal, maximum principal stretch direction is shown here. Right? Now, if you look at these plots, there are two curves here, right? The solid curves is actual as measured from computation. The dotted line is affinity. So affinity worked marvelously well to predict orientation density function. There is nothing here, there's no fudge factors, nothing. We just did the calculation by measuring ODF by looking at the computational results versus taking the original distribution and applying appropriate macroscopic strain. That was a surprise. Now, tortuosity. Tortuosity pretty much measures the deviation from the straight line. And so that's how we started. We started with fibers having kind of tortuosity in all directions, right? And then, again, we subjected to a combination of biaxial tension and shear so that the principal stretch in this direction. Look what happens. There is increase in tortuosity in the direction perpendicular to the stretching. What this means, the fibers not only kind of do not straighten in the direction perpendicular to the maximum principal stretch, but they actually become tortuous, buckling, right? You have buckling and tortuosity. The fibers become straight, right? Now, a couple of things related to applications to experimental data. Okay. Both plots here are experimental, right? On the left, I have orientation density functions for 3 regimes of operating of the spinner, right? If you operate it at a relatively low speeds, you get nearly isotropic distribution. As you increase the speed, right, for the electrospinning device, the distribution becomes more and more anisotropic. Okay. So then materials produced as a result of varying speeds, they were subjected to biaxial tension experiments, and then you can see that, so nearly isotropic, you can see that lambda x and lambda y, right, they're the same, right? But then you could see that for, let's say, highly aligned, there is a significant difference between the two stretches, right? And blue also, right? So this is experimental data. Now, the other thing that is interesting is the following. As you can imagine, these fibers are produced at a very high temperature, right? And when the machine spits them, they're basically liquid, right? The speed produces tension, right? And this tension is part of the processing, right? And high tension probably will produce higher crystallinity simply because it straightens, right? And so it's important to recognize that. And what we did, we tried to tell this story, right, in terms of simulations. But in order to tell this story, again, you have to kind of go and ask yourself some questions about, okay, how this story is obtained. And I want to mention here is the following, that most of the experiments that we've seen in the field are produced using stress control data. And these are typical results for stress control. So for example, if the difference of stresses is 4:1, you will get some pretty weird looking curves. All right? On the other hand, the strain control is much easier to interpret. You see a bunch of straight lines. And so when you interpret the data, not only you have to take into account how material changes, but also dealing with these weird looking curves obtained from stress control experiments. So here's the matching, right? So the solid lines were experimental, solid lines experimental data. These were the best fit experimental things. From computations, right? The points, right? You see some standard deviations, right, on this. Now, the interesting thing about this plot is that in each case, we use different material properties. We couldn't fit it with one property. The property were not dramatically different from a realization to a realization, but they were like 20, 30% difference, right? And the tendency was correct in a sense that we were getting higher crystallinity, stiffer fibers for high velocity spinning machines, and low velocity were getting softer fibers, which is, again, is consistent with our intuition. But it also helps people who produce these things pretty much figure out what's going on, because the way these things are done is you start the machine and then you see what happens, and then you have to backtrack a lot of data, and that's something that is important. Okay, let me summarize what we have here. Okay, pretty much the purpose of creating this was to help understand what is produced. The way this field operates, you produce something and then you try to improve on it. Let's say maybe if you wish, you kind of backtrack with science, right? Manufacturing drives everything, right? And the part where we spent most of the effort and what I present today is trying to explore what really goes on with this fibers. Now, design and optimization of scaffolds. Actually, in my opinion, these scaffolds should be printed in regular structures, and that you can really achieve desired properties, but this that nobody can print them at a size that is necessary for application. So there are no good printing devices right now that will produce polymer scaffolds, let's say micron or submicron in diameter and maybe a 5 to 10 micron spacing. Okay. Also, when we talk about optimizations, we want to kind of look forward and recognize that optimization has to be done not in terms of really mechanical properties, but in terms of improving the ultimate performance of the tissue, so we have to combine the scaffolds with the biomass that will be grown on them. And that's very interesting area because, so one idea that is floating around is to subject the tissue to a constant stress level and then let this to disintegrate as this you transmit high to the cells. It means they exercise at a higher level, and it means its intensity of exercise will improve without really changing the external load, which people feel could be nicely kind of long-term accomplished in patients, right? Whom you don't want to put the patient on a treadmill, right, and ask them to run at a higher rate. Instead, kind of the chemistry of disintegration will produce the effect of a greater exercise, right? The next step will be to really come up with internal state variable macroscopic models. Not an easy task here, again, because it has to be something that, I don't know, manageable for finite element simulations and kind of biomedical needs, right? Because, as I said, it's not entirely clear what parameters are needed to be tracked in such simulations. I mean, other than something that is common mechanics, right? Stiffness and all this good stuff, it's obviously there, but there should be pore sizes, shapes, and so on. And that's something that will be explored. And I think I want to think that's Michael's grant. I started with the Department of Energy. We were working on, believe it or not, they were called TPS, thermal protection systems, for the shuttle. Well, thermal protection system for the shuttle is nothing but a bunch of polymeric fiber with polymeric matrix, right? When we couldn't get data from NASA, we decided that we can as well do it for heart valves. So the same stuff. The temperature is slightly different, all right? Plus it's 6 inches, right? The coating right there. At any rate, computing done at UT, at TAC, and Eric van der Gissen and Eric van der Gissen, right, is the Patrick Onk, forgot Patrick's last name for a second, gave us a version of the finite element code, kind of the first version, and then we significantly modified them, but I want to acknowledge their support and friendship. Thank you very much.
Thank you, Greg. We have time for questions, and if you know, presentation is recorded, so please indicate if you have questions. I'll come with the microphone.
On your experiments and your simulations, did you have this system that had negative stiffness? You said that one that was highly anisotropic?
This one?
Yeah.
No, actually, the way, there is no, okay.
So 4 to 1?
All right, 4 to 1, okay. Let's see. So in this case, what you have two stresses, right? But you have Poisson effect. All right, and this.
So this is the biaxial.
Yeah. This is 4 to 1. This is biaxial stresses, right? And because of the contraction, right? And so if you look at these curves, if you deal with prescribed strains, they're very natural, right? You see they change different angles and blah, 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 and depending on, I mean, it's all straight lines. And I wish people in the biomedical business were running strain control experiments. Then you go from a straight line to it, but they don't. And they have these things, and quite a few papers just attribute the shapes to some complicated physics, but it's not really complicated physics, right? It just, yeah, it's a purely geometric effect. Having said that, fiber buckling happens, right, in biaxial test, right, in the lateral direction. What are they? I mean, we clearly see it. They buckle in plane, out of plane. I mean, it's a full nonlinear geometric problem, right? And so if you have compression, obviously. And if you run a lot of compression, I mean, your test, then you get killed pretty quickly, right? You know, everything starts buckling and you start following, you know, gazillion of buckling fibers, and this is not good for my health, right? Yeah.
In your multi-layer system, you found there is very little difference between a single layer and multi-layers. But these layers were generated as a two-dimensional schemes, right, I imagine. So the connectivity between them, how did you achieve that?
Okay.
Because if they're not connected, then of course that should happen. Right?
Sure. So let's say there is a layer, all right, and there is this adjacent layer, right? And so the fibers have their diameters, right? And I put them next to each other, right? They're within the plane. And anytime there is a fiber from this layer, contacting a fiber from this layer, I denote it as a node, right? The intersection in the finite element business. And these nodes are no different from the nodes within the layer. Right? So if you have, let's say, a layer in the middle, then roughly the number of contacts in such a layer will be 3 times more than the number of contacts in a single layer. All right?
But there will be no fibers going in the perpendicular direction.
No. No. Fibers go out of plane when we deform, right? This happens. But as I mentioned, if you want to start with a genuine 3D problem, you need to start dealing with random walks in 3D, and that's a killer. It's really hard.
I understand that.
Yeah.
Right, right.
Yeah.
The second issue is I've seen presentations where there is tissue adaptation to the stress, how this tissue works. So there is a reorientation of fibers if
Right.
there is a them. This is completely random, it seems to me. So that part of the, for instance, if there is a tissue in the heart valve, and then there are some preferred directions, and most likely the fibers are oriented in some preferential direction.
Right.
I guess you can have it by the probability density. That
Sure, but here's the picture, right? This is the probability density, right, in polar coordinates, right? These are polar plots. And you can see you start with something that is quasi-isotropic. Then you stretch it, right? And that's the principal stretch direction. And you could see that your ODF in this direction, right, is pretty large. And it is pretty small in this direction, right? So
that's as a result of deformation.
Absolutely.
But
Yeah.
But if you repeat that process many times over time, then there will be permanent location of the fibers in the specific directions.
Okay. These are elastic systems.
No, I understand.
Right,
The
and-
assumptions, but in reality, that's what I'm saying.
Yeah, if you... Yes, absolutely. I mean, obviously there will be some viscous effects plus inelastic effects, let's call them. You're absolutely right. They will be aligned. There is no question about it. Yeah.
So I'm really interested in this. I produce carbon nanotubes that look very similar in the nature of the alignment and the porosity that you're getting. You made the statement that that it's easy to determine fiber length. I would love if you tell me how, because we cannot determine fiber length at all. I have grad students that will follow in a TEM and eventually lose one end because they intersect. How are you determining fiber length experimentally?
It's a good question. You know, I don't do experiments, so it's very easy for me. But, you know, okay, let me say this. What is probably hard to control there, right? The fibers break during the process, then they restart the machine. But my understanding is the fiber diameter is pretty consistent. And then more or less, you could take the total mass of the fiber that you use, right, and do the calculations to figure out what will be the fiber length. That's point number one. Let me maybe add the other thing about it. Why orientation density function is easier to measure? Because pretty much I can look at each segment, determine the angle, and then average over the segments that I observe, right? There is no interdependency in measurements for this case, right? The same way I can measure the length of each segment, right? So I come to each segment, I measure the orientation angle and the length, do the sum, and I'll be in a pretty good shape. What is difficult is to say, do these two segments intersect? Because I'm looking at a quasi-two-dimensional picture, right? You know, and interpreting what's in the plane, what is outside plane. That's what makes the visuals hard. If we started not with the geometry, but with mechanics, I probably would not spend any time on geometry because I say, look, if it's tension dominated, I don't care how many intersections I have. I care about the volume fraction and orientation density function.
Yeah, sure.
Yeah. But I can check with the testers. Sure.
Ask you just going back to intersections, because is it possible to replace undergraduate students in the experiment just to simulate 10 layers, and after that to just consider all overlaps, like just two-dimensional patterns, and just compare to experiment, just ignoring that is out of plane, and repeat this experiment many times, and to see what the distribution you get.
So basically
you get the same distribution but simulated by a computer. So if you count all intercept in plane, it doesn't matter where it comes from.
Well, okay, but these are, these are simulation results, right?
Yes.
Okay, and simulation results in theory for those specimens based on the density and ODF, they were perfectly consistent, right? I mean, we reconstructed the data by asking them to do what I just mentioned. They measured segments and blah, 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 and there was no disagreement. And so at this stage, I believe more simulation results based on measured ODF and angles than humans with or without computerized assistance. Because when I looked at the program that was used to do this, this program had a lot of rules, human-based rules. And if it's on Sunday, you have one set of rules, and on Monday it was a different set of rules.
Okay, unless we have some last question, do we? If not, I suggest we thank Greg and continue during the reception. Everyone is welcome. Thank you.
Thank you. All right. I'm ready.
Такие файбры, они рвутся вообще во время